Will quantum navigation replace GPS? What if your car's navigation worked perfectly, deep in an underground parking garage? Or if your phone's map was always pinpoint accurate, even with zero signal? It might sound like sci-fi, but our total reliance on GPS has a critical and frankly scary flaw. It's surprisingly easy to jam or even fake a GPS signal, a vulnerability that's already causing chaos for ships and airplanes worldwide. But a new kind of technology, born from the strange and wonderful world of quantum physics, promises a future of navigation that can't be hacked, works anywhere on Earth, and never has to talk to a single satellite. This is quantum navigation, and it might just make GPS a thing of the past. Section 1. The hidden crisis of GPS. We think of GPS as infallible. It's that silent, invisible utility that powers our modern world. Sure, it gets you to a new restaurant, but it also does so much more. That delivery truck with your package, the ambulance trying to find an address, even global financial markets and telecommunication networks. They all run on precise timing and location signals beamed down from satellites orbiting high above the Earth. But here's the massive problem we're only now starting to confront. The GPS signal is astonishingly fragile. By the time it travels 20,000 kilometers to Earth, it's incredibly faint, weaker than the background noise of the universe. This makes it frighteningly easy to disrupt. There are two main threats: jamming and spoofing. Jamming is the brute force approach, just blasting out a powerful radio signal on the same frequency to drown out the GPS. Suddenly, every device in the area goes blind. Spoofing is far more sinister. Instead of just blocking the signal, a spoofer sends a fake one, tricking receivers into thinking they're somewhere they're not. And this isn't some hypothetical threat. It is happening right now on a massive scale. In 2024, GPS spoofing incidents surged dramatically. Between mid-July and mid-August of 2024, an estimated 41,000 flights were affected by these kinds of attacks. We've seen ships in the Middle East and the Black Sea dangerously thrown off course, and aircraft have had their navigation systems completely scrambled, leading to chaos in the cockpit. A single jamming event in the Baltic Sea impacted over 1,600 aircraft. The problem has become so severe that the United Nations has issued grave warnings about the growing threat to our global infrastructure. Our entire system of logistics, transport, and emergency response is built on a technology that can be knocked offline with relative ease. We've built a modern wonder on a foundation of sand. So, what's the solution? Section 2. The quantum solution. The answer might not come from bigger satellites or stronger signals, but from a fundamental shift in how we think about navigation itself. An answer that comes from the quantum realm. What if, instead of constantly asking a satellite, "Where am I?" Zrение. Ваш девайс только что знал. This is the core idea behind quantum navigation. It's a modern, hyper-accurate version of a very old concept: dead reckoning. Imagine you're blindfolded in the trunk of a car. Even with your eyes closed, you could get a rough idea of where you're going. You'd feel the car accelerate, turn left, and then brake. If you knew your starting point, you could mentally map out the journey and guess your final location. That's inertial navigation. Existing submarines and missiles use this with conventional sensors like gyroscopes and accelerometers. The problem is, tiny errors in these sensors add up. Over a few minutes or hours, that tiny drift can leave you miles off course. This is where quantum mechanics changes the game. Quantum sensors are basically inertial navigation systems on steroids. They are so ridiculously precise that they can run for hours or even days with almost zero drift. How do they pull this off? The secret lies in one of the strangest ideas in physics: the fact that a single atom can be in multiple places at once. It's called superposition. To harness this, scientists use lasers to cool a cloud of atoms to just a fraction of a degree above absolute zero, the coldest temperature possible in the universe. In this extreme state, the atoms become perfect quantum sensors, incredibly sensitive to their surroundings. As a vehicle carrying these supercooled atoms moves, accelerates, or rotates, the quantum state of the atoms changes in a predictable way. By measuring these tiny changes with lasers, the system can calculate its own movement with breathtaking accuracy. It feels every tiny jiggle, every subtle turn. It doesn't need to look outside. It just knows. It is the perfect dead reckoning machine. Section 3. How is this unhackable? The biggest promise of quantum navigation is that it's inherently secure against the kinds of attacks that plague GPS. It's not just hard to disrupt, it's fundamentally immune to jamming and spoofing. The reason is simple. There's no signal to attack. A quantum navigation system is entirely self-contained. It doesn't receive any external signals at all. It's a passive system, a silent observer. Think of it like navigating with a map and compass, but where the map is the fabric of physics itself and the compass is a cloud of atoms. You can't jam the laws of physics. You can't spoof an atom. GPS by its very nature is vulnerable because your device is just a passive listener, waiting for a whisper from space. A spoofer just has to shout louder with a more convincing lie. A quantum system, on the other hand, isn't listening to anyone. It's generating its own position data from within. This makes it the ultimate stealth navigation tool. A vehicle using it is completely electronically silent, broadcasting nothing and receiving nothing. For military applications, this is a revolution. Drones, ships, and aircraft can navigate in complete secrecy. For the rest of us, it means a future where your navigation is 100% reliable, all the time, no matter what. It's a system you can trust implicitly because its security is guaranteed by physical law, not by complex breakable code. Dar. Section 4. The breakthroughs making it real. This might all sound like something from a distant future, but these breakthroughs are happening right now. For decades, quantum sensors were the size of a room, fragile lab experiments that required a team of PhDs to operate. But that is changing, and it's changing fast. The Australian company Q-CTRL, a leader in this field, has been running stunningly successful field trials. In recent tests, their quantum-based navigation system performed up to 50 times better than the high-end military-grade inertial systems that are currently the best backup for GPS. That's not a small improvement, that's a generational leap. They've tested these systems in the real world, on the ground and in the air. In one world-first trial with the Royal Australian Navy, they put a quantum gravimeter, a device that measures tiny changes in the Earth's gravity, onto a moving naval vessel. The sensor, which took up about the space of a server rack, ran continuously for over 144 hours during real maritime operations with zero human intervention. It was successfully navigating by reading the invisible hills and valleys of the Earth's gravitational field like a map. Another wild method uses quantum magnetometers to read the unique magnetic signature of the Earth's crust. It's like a geophysical fingerprint. The Earth's magnetic field has unique patterns and anomalies, and a sensor that's sensitive enough can read these patterns, compare them to a map, and figure out its location. One of the biggest hurdles has always been noise. These sensors are so sensitive they can be thrown off by a truck driving by or the hum of a ship's engine. But here, too, there's been a breakthrough. Artificial intelligence. QCTRL and others are using smart machine learning algorithms that act like noise-canceling headphones for the sensor. They filter out all the environmental vibrations and interference to isolate the true motion of the vehicle. This software ruggedization is what's finally letting these delicate quantum systems leave the lab and work reliably in the messy, noisy real world. Section 5. The future is here, but not everywhere. So when can you get a quantum navigator in your car or your phone? Well, don't hold your breath just yet. The first adopters will be in high-stakes industries where the cost is justified and the need for absolute reliability is everything. The military is the most obvious customer, with the US, UK, and Australian Defence Forces all running trials. Autonomous vehicles are another key area. A self-driving truck or a flying taxi simply can't afford to lose its navigation in a tunnel or a city. quantum guidance could be the unbreakable lifeline they need to operate safely. We'll also see it in commercial aviation as a foolproof backup against spoofing, and in maritime shipping, where vessels can navigate for weeks without a single satellite ping. For the average person, there are still a few challenges to overcome. The big three are size, cost, and power. While these systems are shrinking fast, a device the size of a server rack is still a long way from a chip in your smartphone. And the power consumption, while impressive for what it does, one naval system used less power than a toaster, is still way more than a tiny GPS chip. The most likely path to your pocket will be a gradual one. Just like quantum research is leading to new wearable medical sensors, we'll see specialized quantum devices first. The market for these sensors is projected to grow to over $2 billion by 2045, driven by these niche applications. Over the next decade, the tech will continue to shrink, and the cost will fall. Then, maybe in 15 to 25 years, a quantum-based sensor could become a standard component in our phones and cars, working seamlessly alongside GPS. Your phone might use GPS when it has a clear signal, and then instantly switch to its internal quantum sensor the moment you enter a subway, without you ever noticing the difference. So, while we wait for a quantum compass in our pockets, the pieces are already falling into place for a navigation revolution. What do you think is the most exciting application for this technology? Autonomous cars, deep-sea exploration, or something else entirely? Let me know down in the comments. And if you want to stay ahead of the curve on the tech that is changing our world, make sure to subscribe. Quantum navigation isn't going to make your GPS obsolete tomorrow. For most of us, most of the time, the system we have works just fine. But this new technology patches GPS's most critical holes: its vulnerability to attack and its inability to work everywhere. It represents a whole new level of resilience. For a generation, we have navigated by looking up at the sky, relying on a faint signal from a distant satellite. The next generation of navigation will come from looking inward, listening to the subtle, complex, and unshakable quantum hum of the universe to find our way. The real question isn't just about replacing GPS. It's about what new possibilities open up when we can navigate anywhere, with perfect accuracy and total security. What other parts of our world will the quantum revolution transform next?